Hello students, my name is Dr. Antonio Hajianya and I'm your Physics 101 lecturer for this topic. In this video clip, we want to look at Kepler's laws of planetary motion. But before we go into the topic fully, let us first understand what the plane figure ellipse is, because this ellipse is a figure of importance in this topic. An ellipse is a plane curve surrounding two focal points such that for all points on the curve, the sum of the two distances to the focal points is a constant. Look at figure 1 for illustration. Using figure 1, some of the characteristics of an ellipse include: number 1, for any point on the curve, the sum of the distances PF1 and PF2 is a constant. That is, P1F1 plus P1F2 is equal to P2F1 plus P2F2, which is equal to P3F1 plus P3F2, which is equal to a constant. Number 2, the line from A to B, which passes through the foci and the center O, is called the major axis, while the line from C to D is the minor axis. The distances AO is equal to BO, F1O is equal to F2O, and CO is equal to DO. So with this knowledge, let us now go into the Kepler's laws of planetary motion. Kepler's first law. Kepler's first law states that the path of each planet about the Sun is an ellipse, with the Sun at one focus. Look at figure 2 for illustration. Here, the Sun is positioned at focus F1, and the planet P moves in an elliptical orbit around it. The sum of the distances PF1 and PF2 remain constant. Kepler's second law. Kepler's second law states that each planet moves such that an imaginary line drawn from the Sun to the planet sweeps out equal areas in equal periods of time. Take a look at figure 3 for illustration. This means that if planet P moves from point 1 to point 2 in time T1 and sweeps out an area A1, and then moves from point 3 to point 4 in time T2 and sweeps out an area A2. Then, if T1 is equal to T2, A1 is equal to A2. Another implication of this is that The closer a planet is to the sun, the faster it moves. Let's look at Kepler's third law. Kepler's third law states that the ratio of the squares of the periods of any two planets revolving about the sun is equal to the ratio of the cubes of their semi-major axes. Recall that the semi-major axis S is half the major axis of the orbit as shown in figure 2. The semi-major axis represents the planet's mean distance from the sun. Now let us look at the mathematical implication of the third law. If T1 and T2 represent the periods of any two planets, and S1 and S2 represents their semi-major axis, then T1 over T2 all squared is equal to S1 over S2 all cubed. This equation 1a can be rewritten as shown in equation 1b. This means that S cubed over T squared should be the same for each planet. Derivation of Kepler's third law from Newton's laws. Kepler's third law can be derived from Newton's law of universal gravitation and second law of motion as follows. Sigma F equals mass acceleration. This is from Newton's second law. And G times M1 ms over ρ1 squared is equal to M1 times V1 squared over ρ1. If you look at this is the gravitational force, and this is the centripetal force on the planet with mass M1. So the given parameters in this equation 2 are that G is the gravitational constant, M1 is the mass of the particular planet, ms is the mass of the sun, ρ1 is the distance of the planet from the sun, and v1 is the planet's speed, which is given by v1 equals 2 pi r1 over t1. We now substitute this equation into equation 2 and get that G m1 ms over ρ1 squared is equal to m1 into 4 pi squared r1 over t1 squared. This equation can be rearranged to get equation 3. This means that for planet 1 and planet 2, T1 squared over R1 cube is equal to T2 squared over R2 cube and is equal to 4 pi squared over GMS. Therefore, from this we get that T1 over T2 all squared is equal to R1 over R2 all cube, which is the Kepler's third law. Now let's solve some examples. Example 1. The period of mass was first noted by Kepler to be about 687 days, which is 687 days divided by 365 days, which gives 1.88 year as measured from Earth. Determine the mean distance of mass from the sun using the Earth as a reference. Take the Earth-Sun mean distance (RES) to be 1.5 times 10 to the power 11 meters. Solution. To solve this problem, we let RMS be the mass-sun mean distance and use the Kepler's third law. That is, RMS over RES is equal to Tm over Te, or to the power 2 over 3. From here, we get to make RMS subject to the formula and get that RMS is equal to RES times Tm over Te, all in bracket, to the power 2 over 3. So if we put in the given quantities, we'll solve to get that RMS is equal to 2.28 times 10 to the power 11 meters. Example 2. Determine the mass of the Sun given the Earth's mean distance from the Sun as RES is equal to 1.5 times 10 to the power 11 meters. And the Earth's period TE is equal to 1 year, which is equal to 3.16 times 10 to the power 7 seconds. Solution. To solve this problem, we use the equation Te squared over RES cubed is equal to 4 pi squared over GMS. We make MOS subject to the formula and now put in the given quantities and solve. So if we do this, we'll get MOS to be equal to 2.0 times 10 to the power 30 kg. Thank you for watching this video lesson. For further studies, consult the recommended textbooks as listed here.